Okay, we're going to be looking at infrared spectroscopy. Infrared spectroscopy has the energy of light that causes bonds to vibrate. And because each individual type of bond has a specific wavelength that it absorbs, what we find is we can actually see what type of functional group is on the molecule in infrared spectroscopy. The first thing we need to do is review light. Light is, of course, electromagnetic radiation. And it's basically a package of energy that is defined by the wavelength, or you can use the frequency. How are wavelength and frequency related? Frequency, nu, is equal to c, the speed of light, 3 times 10 to the 8 meters per second, over the wavelength in meters. Why is it we need to do that to understand this? Is because we'll start referring to the wavelength or frequency of light. And so you need to realize that wavelength is basically the distance from peak to peak. And so if this is really long, there's very low energy. If it's really short, there's very high energy. Likewise, frequency indicates energy, but it's instead of being the inverse as wavelength is, its frequency is how often you're having a cycle going from down to up, like this, from up to down to up is one cycle. How many of those you have per second? And the more it's vibrating very fast per second, that's more energy, rather than very slow, it's low energy. So as frequency decreases, the energy decreases. So when we start talking about light, remember this relationship. We use the electromagnetic spectrum. We use various forms of light in spectroscopy. We use radio waves, which are really, really low energy. We use that in NMR. There is some microwave radiation analyses that we do, but these are low energy also. It's not common in the analysis of molecules to use microwaves. We will be using in this slideshow infrared radiation, and we'll talk about that in just a little bit. Visible light is what you can see. It's higher energy than infrared. Then you have ultraviolet radiation. Now with this, we're talking about the energy of breaking a double bond and promoting the electron in the double bond up to a high energy anti-bonding situation. So this breaks a bond. And then we have X-rays, gamma rays, and cosmic rays. These are called ionizing radiation because they have enough energy to knock an electron out or otherwise do very damaging type of changes in molecules. X-rays and gamma rays are used to ionize molecules, as in doing a mass spec. We ionize things using light like that. But what we're going to talk about in this slideshow is infrared radiation. This type of radiation is what makes things feel warm. So if you're sitting in front of a fire, not so close that you can actually get molecules from the fire hitting you and warming you up, but let's say you're sitting 5 or 10 feet from the fire and you feel the fire, what you're actually feeling, the heat that you feel, is infrared radiation. And this is the radiation that actually causes molecules to vibrate faster. So that's what we're going to look at. In all of our spectroscopies, except for mass spec, what we do is we shine light on the sample. Some of this light is absorbed depending on the sample, and then we look at the light that comes out. And when we detect it, we report either how much is transmitted, which is a percentage of how much comes in, like 80% or something, or we will report how much is absorbed. If 80% is transmitted, then 20% is absorbed, etc. So that's what we do in a spectrometer. So now what we're going to do is we're going to look at what happens with infrared spectroscopy. Infrared spectroscopy has the energy of light that allows us to identify functional groups, because this is going to be causing the bonds to vibrate, and we can then look at the individual bonds and see characteristics of them. We're also going to look at UV spectroscopy, which tells us about double bonds, and we're going to be looking at NMR spectroscopy, which lets us look at the structure of a compound by seeing where the nucleus resides with respect to the electrons. So we're actually looking at the energy of the nucleus in a magnetic field with respect to how the electrons prevent it from seeing the magnetic field or not. But we'll go to those later. Right now, infrared. Infrared spectroscopy is because bonds will absorb light to vibrate at a higher energy level. Normally, bonds are vibrating in ground state vibrational energy level, and if you shine infrared light on them, they'll bounce up to a higher energy level. Of course, then they fall down again. So what we see are specific energies associated with specific bonds, and so then we know a little bit more about what's inside that molecule. In infrared light, bonds that are polar can absorb the infrared light. If you have a bond that is symmetrical, for instance, a double bond that has the same groups on each side of the double bond, you will find that it's symmetrical and it doesn't absorb infrared light. We call it infrared inactive. The greater the polarity that's in the bond, the greater the probability of absorption. So something like a carbon-hydrogen bond, which has some polarity in it, it's not hugely polar, but the difference in electronegativity is 2.5 on carbon and 2.1 on hydrogen. That's polar enough that it can absorb in infrared light, but the probability of it absorbing is lower than that, for instance, a carbon-oxygen bond, which is much more polar. So when you have the very polar bonds, they tend to absorb and have a larger intensity peak from just a single bond. We do not use frequency or wavelength when describing infrared spectra. We use instead wave numbers. Wave numbers are the frequency divided by the speed of light. So if we look back at that equation where it's frequency equals c over lambda, a wave number is the wave 1 over the wavelength. So if I want to figure out what 1 over the wavelength is, I just take the speed of light and divide both sides by it, and you get that 1 over lambda is equal to nu over c. No big deal, and we're not going to do any calculations with it. What we end up with is units of centimeters to the -1. The range of wave numbers that we look at in infrared are from 4,000 centimeters to the -1 to 400. That's the range that we limited to, and really the most important range of that is even narrower. So let's go ahead and look at what the peaks that we can see. When we're in the 3,400 to 2,800 range, that's where we're going to see atom to hydrogen bonds. So oxygen to hydrogen, nitrogen to hydrogen, and carbon to hydrogen. This number, 3,400, actually can go as high as 3,600. That's kind of low for what we would say is the true range here. So keep in mind that it can go above 3,400 really. But notice these are the bonds to hydrogen. When we have carbon nitrogen bonds or carbon bonds that are triple bonds, they're around 2200. So it's showing here 2250 to 2100, and I just think 2200 when I think that. And of course you can go a little bit to either side. Carbonyls, carbon nitrogen double bonds and carbon bonds are from 1850 to 1600. The range that is most important to us is for the carbon oxygen double bond, and that goes from 1800 down to just under 1700, at like 1680 is the lowest the carbonyl will go. The carbon bonds are from the 1680 and lower. You don't see too many molecules with a carbon double bond to a nitrogen, but they exist. They're called imines. At below 1600, what you see is a lot of single bonds, and those single bonds are what we call the fingerprint region, and that's because these are very hard to look at an individual spectrum and actually assign individual peaks to types of bonds. In the first 3 sections that we went through, it's relatively easy to look at a spectrum and say, oh, that peak right there is an oxygen-hydrogen bond, or that peak right there, that's a carbon-carbon bond. But when you get below 1600, it's very hard to assign individual bonds to individual peaks. The fingerprint region is right here. It's from right here, 1600 and below. And just even tiny changes in the structure of the molecule will make the fingerprint region change. So the red spectrum here is 1,2-dimethyl cyclohexane that is cis, and the blue one is when it is trans. And you can see, look, see how this peak here isn't there, but this one's shifted over to here? Look how this peak shifts over there. Look how the intensity of this one is bigger than that, but the intensity of this one is smaller. This region down here is a unique fingerprint that we do not say that the molecule is the same unless each peak matches wave number to wave number, intensity for intensity. So it has to be pretty much an exact match. Now, if you have more samples, sometimes you get deeper peaks, but they all will get deeper in the same amount for a bigger sample. The wave number for the individual bonds change by 3 different factors. Stronger bonds have higher frequency, which means higher wave number. Smaller mass atoms have higher frequency vibrations, and so they have higher wave number absorptions. And the bending are very low frequency absorptions. Pretty much all of the useful bond absorbances are the stretching because they're way above the fingerprint region. The bending are down in the fingerprint region. There are 2 things that will affect the intensity of a peak. We already discussed bond polarity. The more polar a bond, the greater the probability is that it will absorb a particular wavelength of light that it absorbs, its specific wavelength of light. So if I look at a carbon-carbon bond, it's going to have a very small peak compared to a carbon-oxygen bond. Carbon-oxygen bonds are very intense. The polarity of a carbon-carbon bond, you would think that it would be infrared invisible, but if it's not a perfectly symmetrical carbon-carbon bond, there's different groups on either side of the double bond, that is enough to cause it to be infrared active, but their peaks are small because it's not very polar. The other thing that will cause a peak to become more intense is to have more bonds. So even though a carbon-hydrogen bond is not very polar, there are lots of them in most organic molecules, and so you'll have a pretty big peak. For instance, if you think back on the cyclohexane spectrum that you just saw, the carbon-hydrogen peak around 3000 was really, really intense, and that's because there were lots of carbon-hydrogen bonds. So when we compare, let's say, right here we have hexabromopropane, there's only 2 hydrogens, so you're going to see a teeny tiny peak for the carbon-hydrogen stretch. Whereas in decane, you have so many carbon-hydrogens, you see a huge carbon-hydrogen peak. Okay, if a bond has no dipole, it will be invisible. And this molecule right here is an example of that. The carbon-carbon double bond is invisible when the groups on either side are the same. So this is a perfectly symmetrical molecule. So this bond right here is invisible or infrared inactive. You would see the carbon-hydrogen stretch peaks, but this bond itself, you would not be able to detect that functional group. But of course, now when there's a large dipole, it's going to be a strong peak. We rate the peaks as being weak, medium, or strong. And so a weak is pretty tiny peak. Medium maybe is like a 50% intensity or maybe slightly less. And then strong is where it's one of the bigger peaks in the spectrum. We'll only look at a few functional groups here. In this chapter, we're going to see alkynes, alkenes, alcohols, and carbonyls, and we also will look at the carbon-hydrogen absorptions. And as we cover more functional groups later on in the book, we're going to look at their absorbances in IR. Whenever you look at infrared, you will be able to break down the regions into single bonds of to hydrogen, triple bonds in this region, and double bonds in this region. So this is a useful way of analyzing your spectrum. Spectrum is going ahead and grouping them like this so as to help yourself remember what peaks mean what. The fingerprint region, some people will say it's 1600 and below. Some people will say it's 1500 and below. It's kind of just in that general range. Remember that the fingerprint region is always truly a fingerprint for a specific molecule. Here's an example of nonane. Here is that 3000 line. To the right of this, lower than 3000 centimeters to the -1, you have the carbon that is sp3 to a hydrogen. This is where we see this. All of the carbons in nonane are sp3. So these are where those carbon-hydrogen bonds are absorbing. Here, we have the fingerprint region is starting right about here. So all of these are single bonds in this molecule. And again, it's a fingerprint. Now there's some people who analyze these and assign, let's say, this to a carbon-hydrogen bending and this to a carbon-hydrogen in a particular place. We're not going to do any of that. Really, what you need to do is be able to assign specific peaks up here and then realize that all this is the fingerprint region, and it has to match peak for peak, intensity for intensity. The carbon-carbon double bonds, they absorb in, let's say, 1640 to 1680. So we're looking at the carbon-carbon double bond stretch that's in this range. Right about 1675, just above that, is where the carbon-oxygen double bonds start. And so you might think that there would be a little confusion there, but the difference is, notice these are all medium, and this one's even weak. Okay, so you don't have to realize, see, these are asymmetrical double bonds, and these are more symmetrical. So these are weak, those are medium. You don't have to worry that the carbon-carbon bonds are going to overlap with the carbon-oxygen double bonds, because really there's a cutoff right there, right at 1680, 1675. (1650) is what you want to remember for the carbon double bond. Is kind of like an intermediate range for the carbon-carbon double bonds. At the 3000 line, you need to remember this as an important dividing point, just as 1680 is an important dividing point between the carbon-carbon double bonds and the carbonyl. At 3000, you divide between carbon that is sp3 to hydrogen on the low side of this, and carbon that is sp2 to hydrogen on the higher side of it. So from 3000 to 3200, you find the carbon sp2 to hydrogen. And then even higher, you find the carbon that is sp to hydrogen, as in a terminal alkyne is where you will see this. So that's at 3200 to 33. And again, the overlap is not there, so you really can look at this and say, oh, that's a cutoff line. Here's an example. Here is the 3000 line. This is a carbon-carbon double bond to hydrogen. So this is the carbon that is sp2 to a hydrogen. This is not the carbon-carbon double bond. This is the hydrogen that's on the carbon-carbon double bond. These are all peaks that are sp3 carbons to hydrogen. So that's all these carbons over here. And then look at this peak right here. This is right below 1650. So that's a carbonyl. And notice, a carbon-carbon double bond. And so notice that it's not hugely strong. If this were a carbonyl, as we see, it will be going very, very deep, and it's going to be kind of wide in the spectrum too. The carbon-carbon double bonds, they tend to be sharp. The carbonyls tend to be wider and deeper. This little peak right here is an overtone, and you don't have to really worry about identifying it. It's not really anything up there. You often see these with the alkenes. Okay, here's an example of a nearly symmetrical alkene. It's slightly asymmetrical because this is different from this, and so there's some asymmetry here. So you get a little teeny tiny peak, but it's a pretty symmetrical molecule, so it's very, very weak. You can see here, this is the hydrogen that is on the double bond, right there, that little peak. And then from 3000 to below, those are all the carbon hydrogens that are here and here on the sp3 carbons. Aromatic rings have similar carbon sp2 to hydrogen, and so you can't really distinguish between an alkene or an aromatic in the carbon hydrogen absorption. However, aromatic rings have some overtones that are really easy to see and easy to recognize. They're weak, but they're specific at this 2000 to 1660 area that really is kind of unique. We'll look at that. They also have the carbon-carbon double bond absorption down here. But these are weak, and they're kind of easy to see usually. They can be very useful in helping you recognize an aromatic compound. The carbon-carbon double bond you will see, but it'll be a medium peak and not weak. And oftentimes it's going to be sharp. However, if you have a carbonyl there, it might kind of be overridden by it. We'll take a look at some spectra. Okay, here is an example of an oxygen-hydrogen stretch peak. Right here, you can see it's at about 3375 or so, 3370. Notice how broad it is. That is what makes an oxygen-hydrogen easy to recognize, because you see a deep, broad absorption right here in this general range. Notice there's no absorptions between here, so that's screaming out no carbonyls, no carbon-carbon double bonds, no nitrile, no alkyne. But we do have the carbon hydrogens for carbon sp3 to hydrogen right there. This is an important thing to note. Notice that you have this sharp peak right here next to the oxygen-hydrogen stretch. That sharp peak is for a dilute solution. The reason that alcohols have a very broad peak is that they hydrogen bond, and when hydrogen bonding occurs, it actually weakens the oxygen-hydrogen bond. And at any one time, when the infrared light passes through, there are various states of hydrogen bonding, and so here you might have very little hydrogen bonding. Here it's almost completely hydrogen bonded. This peak right here is no hydrogen bonding at all. So you get this broad peak from hydrogen bonding. This is from no hydrogen bonding. Notice what happens when you start diluting down the solution. You start getting less of the broad peak and more of the oxygen-hydrogen bond that is not hydrogen bonded. Carbonyl peaks are very polar and very intense absorptions. You can actually quantify which type of carbonyl you have. We're not going to do that quite at this point in time. Just realize that you can look those up and determine what type of carbonyl you have. Aldehydes have a special little peak because they have a hydrogen on the carbonyl. There's a special little peak for that carbon-hydrogen bond. Here is a carbonyl. Notice it's at 1727 centimeters to the minus 1. Notice how deep and intense it is. And it's not really sharp. It's a little bit broader than some of the other peaks. That's very typical for a carbonyl. However, what else does it show? It shows this peak at about 1720 right here, 1719. That is the carbon-hydrogen aldehyde peak. And so this is indicating an aldehyde is there. Notice right here, we also are showing an OH peak. That's really, this must be an aldehyde that has an alcohol group on it also. Notice, here's the 3000 level. Because there's no peaks over here, we can say, oh, this is a saturated aldehyde. Here's a ketone. Notice you do not see that aldehyde peak here because it's a ketone. What do you see? An intense carbonyl. This little peak that you see right here, this is an overtone for the carbonyl. So you don't have to worry about ever identifying it, but this isn't an alcohol peak right there. That's an overtone for this carbonyl. You see overtones in other places too. Here is an ester, ethyl octanoate is an ester, a saturated ester. Here is that carbonyl, no aldehydic proton, no carbon double bond hydrogens, no carbon double bond over here. There's that little overtone for the carbonyl. Don't worry about it. The carboxylic acid OH bond is very broad because carboxylic acids do a special thing forming a dimer, which will learn about in a later chapter. They broaden out their oxygen-hydrogen bond absorption very much. So whenever you see an OH bond that goes all the way over to about 2300 like this, you can feel pretty sure it's a carboxylic acid. This is so intense, it almost obscures all the peaks here. You really can't know much about this. You can feel that this is probably all saturated and that there's no unsaturation here. You can reconfirm that by looking down here at around 1600 and not really seeing a peak there. So it looks like it's saturated, which it is. It's hexanoic acid, so there's no double bond in there. So you look at the spectrum and try to identify what functional groups does this molecule contain. Okay, if I look, you can see there's this bond on the left side of 3000. So that indicates to me there's a hydrogen on a carbon-carbon double bond in there. Now you don't see any kind of peak over here indicating a sharp peak for a carbon-carbon double bond. So it's probably an internal double bond, not a terminal one. Try to analyze this and find out what functional groups you see here. Okay, if you look, right, it ought to hit you in the face right here that you've got an alcohol group. Likewise, there's this sharp peak right here. Where exactly is this? Well, this is the 3000 line, so that's on the 3100 line. That's for a hydrogen on a carbon-carbon double bond. And if we look over here, we see that carbon-carbon double bond right there. So this is probably a terminal ene, and it's got an alcohol on it. That right there, you're seeing an overtone. Don't worry about it. So what functional groups do you see here? Well, first off, always recognize what you don't see. You don't see an alcohol peak here. You don't see a carbonyl here. That's important to note. What you do see is a hydrogen on a carbon-carbon double bond, and you see a carbon-carbon double bond right here. So most likely this is a terminal carbon-carbon double bond. It could be that it's asymmetrical, and so you've got this intense peak from a good bit of asymmetry. But there's also a good chance it could be a terminal terminal alkene. What functional groups does this one have? Okay, when we look at this, you can see that right here we have an alcohol, and the 3000 level, 3000 line is right there. This might be an alkene. It's just over the 3000 line, so I believe it's an alkene. And this small peak right here kind of confirms that. So I would say this is an alkene with an alcohol group on it.